Okay, this next one has you draw the Lewis structure of H2O and determine all of these properties on the right-hand side of the screen. If you're in introductory chemistry, we'll stop at deciding whether it's polar or non-polar. And if we're in general chemistry, we'll do all of this stuff. So the first thing I'm going to do is count up valence electrons. I've got 2 hydrogens, 1 each, so that's 2. I've got a oxygen, and that's 1 of those for 6, so the total is 8. So the next thing I'm going to do is I'm going to draw the molecule, or at least I'm going to draw the atoms on the piece of paper as symmetrically as possible. And then I'm going to draw 1 bond between each of the atoms in the central atom. Once I've done that, I'll reduce the number of valence electrons in my count by the number that I used in the bonds, 2 bonds, 4 electrons. And then I'll recount and I have 4 left. Now, I know that hydrogen is okay as far as octets are concerned, but oxygen still needs 4 more electrons. So I'm going to do that in terms of lone pairs. Now oxygen has an octet, and if I were to reduce my count even further, I would see that I ran out of electrons. Now I'm at 0. Okay, everybody has octets. I'm out of electrons, and so I'm done. Now the rest is figuring out what these properties are based on the Lewis structure. If I look at the central atom oxygen, I notice that there are 4 geometry groups. 2 of the geometry groups are lone pairs, and 2 of the geometry groups are bonds to hydrogen. So the 4 geometry groups mean the electron geometry is tetrahedral. Now, it has 2 lone pairs. So the molecular geometry, the geometry considering only the bonds, would be considered bent. From an electron geometry of tetrahedral with 2 lone pairs, the molecular geometry is bent. From that electron geometry, I can determine the bond angles are 109.5 degrees, or specifically, I could even say less than 109.5 because of the lone pairs. And if I were to decide whether or not it was polar or non-polar, I could say that it is polar. Remember, the quick and dirty way to do that is to decide if all the geometry groups are the same. They're not all the same. 2 lone pairs, 2 bonds to hydrogen, they're not the same. So it's polar. In other words, the bond dipole moments do not cancel. All right, that's it if you're in introductory chemistry. Let's move on. If you're in general chemistry, the intermolecular forces are going to be based on the fact that it's polar. Of course, everything has dispersion forces. And also, it's going to have dipole-dipole forces because it's polar. Now, notice that the bonds are made of oxygen-hydrogen bonds. And that's one of the 3 bonds that will give you hydrogen bonding. Oxygen-hydrogen bonds, nitrogen-hydrogen bonds, and fluorine-hydrogen bonds will all lead to a special, really strong intermolecular force called hydrogen bonding. So that will also be present. Hybridization, we can determine based on the electron geometry, and the electron geometry is sp3 is tetrahedral, so that means sp3 hybridization. And counting bonds gets us the number of sigma and the number of pi bonds. Single bonds are sigma bonds, so there's 2 of those, and there are no double bonds or triple bonds, so there's 0 pi bonds. Okay, that's it.